Hey guys, in this video we're going to go through a harder example of using integration by substitution to solve a definite integral. So this question is taken from a Cambridge P3 exam. The question is basically find the definite integral from x equals 0 to x equals 1 of the function 1 minus x squared divided by 1 plus x squared, and then that whole thing squared, and we're integrating with respect to x. So we know that this is the same as a of 1 minus a of 0, where a of x is actually the antiderivative of that same function of 1 minus x squared divided by 1 plus x squared dx. Okay, and we're given a hint to solve this question. The hint is use the substitution x of theta is equal to tangent of theta. So we're told to use the substitution x of theta is equal to tangent of theta. Let's recall our rule so we don't forget the theorem of integration by substitution. Theorem goes like this. The antiderivative of the function y of x dx is actually equal to the antiderivative of the function y of x of theta times x prime of theta d theta. It's written a little differently. Don't get too confused about the x's and the thetas. Last time, in the last video, I had a u here and a du here. Don't worry about that. These are just labels. I can swap them around however I like. So that's our theorem of integration by substitution. We're going to use that to solve this problem. Notice we're starting with y of x dx. That's what we're starting with. So we're starting on this side here. So we're going to go that way. That's the direction we're going to go in. We're going to make the substitution x of theta. So we're going to have y of x of theta on that side, where x of theta is going to be equal to tangent of theta. And so that means if we really want it to be equal to the antiderivative of y of x dx, we should multiply by x prime of theta before we can put that d theta on the end there. So don't forget to multiply by x prime of theta. It's very important, otherwise we're not using the theorem correctly. Okay, let's get started. So, how should we do this? Well, the most useful thing to calculate first is actually x prime of theta. Now, all we need to do to calculate this is differentiate tangent of theta and go back and check the differentiation of trigonometric functions. If you've forgotten how to do this, it's actually just 1 over cosine of theta squared. So it's 1 over cosine of theta squared, which another way to write that is secant of theta squared. But I'm just going to keep it as 1 divided by cosine of theta squared. Okay, so let's get started. So we know that y of x is equal to 1 minus x squared divided by 1 plus x squared squared. That's one thing we know. Another thing we know is that cosine of theta squared plus sine of theta squared is equal to 1. That's going to come in handy. And if we take this and we divide through by cosine of theta squared, then we're going to end up with, well, cosine of theta squared divided by cosine of theta squared is 1, plus sine of theta squared divided by cosine of theta squared. Well, that's actually tangent of theta squared. And this is equal to 1 divided by cosine of theta squared. Well, that's the same as x prime of theta. So x prime of theta is 1 divided by cosine of theta squared. So we know that x prime of theta is actually equal to 1 plus tangent of theta squared, and of course that's equal to 1 divided by cosine of theta squared. Alright, so that's a couple of key points. Let's go ahead and make our substitution now. So when we substitute in, we're taking this guy right here, 1 minus x squared divided by 1 plus x squared, and then that whole thing squared dx. We're going to make the substitution x of theta equals tangent of theta. So we end up with the antiderivative of 1 minus tangent of theta squared. So we just plugged in x equals tangent of theta to the top part there. And we're not worrying about the definite integral at the moment. We don't care about this because we need to find the antiderivative function first. So then we can get a of 1 minus a of 0. So we don't need to worry about the definite integral for now. On the bottom, we've got 1 plus x squared, so 1 plus tangent of theta squared. And then that whole thing is squared. And of course, we're going to multiply this by x prime of theta, d theta. Okay, and so this is equal to the antiderivative of, well, we don't have any special way of writing 1 minus tangent of theta squared on top, so we're going to leave that alone, 1 minus tangent of theta squared. But on the bottom, what we just worked out before is that 1 plus tangent of theta squared is the same as 1 divided by cosine of theta squared, which is exactly x prime of theta. So what we've got on the bottom is 1 divided by cosine of theta squared, and that's being squared because we've got 1 plus tangent of theta squared, and then that whole thing's squared. And we're multiplying by x prime of theta, so we're going to be multiplying this whole thing by 1 divided by cosine of theta squared, d theta. And so now we're going to be basically cancelling out one of these cosine of theta squared rather, because we're dividing by 2 of them and then we're multiplying by 1 of them. So that's going to cancel with one of them on the bottom. So that's what we're really left with. We're left with the antiderivative of 1 minus, we're left with the antiderivative of 1 minus cosine of theta, we're left with the antiderivative of 1 minus tangent of theta squared divided by 1 divided by cosine of theta squared, and then d theta on the end there. Let's go to a new board and write that out. So here's where we're at now. We have the antiderivative of 1 minus tangent of theta squared, tangent of theta squared, divided by 1 divided by cosine of theta squared, d theta. And when you divide by fractions, you just flip the fractions up and multiply them. So that is, of course, equal to the antiderivative of cosine of theta squared times 1 minus tangent of theta squared, d theta. We're nearly done because, well, this is equal to the antiderivative of cosine of theta squared times 1 minus sine of theta squared divided by cosine of theta squared, d theta. When we multiply through by cosine of theta squared, these two are going to cancel, and we're just going to be left with the antiderivative of cosine of theta squared times 1 minus cosine of theta squared times sine of theta squared divided by cosine of theta squared. So as we said before, those will cancel, and we'll just be left with sine of theta squared d theta. Now we need to use a trigonometric identity. You can go pull up a list of trig identities, and that list will tell you that actually cosine of theta squared minus sine of theta squared is actually equal to cosine of 2 theta. So this thing right here is just equal to cosine of 2 theta. And so this whole thing collapses down to the antiderivative of cosine of 2 theta, d theta. Now this one, we know exactly how to do. This one is nice and easy. Just use reverse chain rule or, I don't know, easier substitution, however you want to do it. I'm just going to do it off the top of my head because I know that when I differentiate sine of 2 theta, I'm going to end up multiplying by 2. So I want to cancel out that multiplication by timesing it by half. So the antiderivative must be 1/2 of sine of 2 theta, because again, when I differentiate this thing, it's going to become cosine of 2 theta, and then I'm going to be multiplying by 2. So that half will cancel out. So it's 1/2 of sine of 2 theta plus the constant of integration. Okay, we've nearly found our function a of x. Well, what we have here is actually a of x of theta. Now remember, if we go back to, well, what the problem was at the start, we actually want a of 1 minus a of 0, where a is expressed in terms of x. So that's very important. We can't just plug in theta equals 1 and theta equals 0. We need to put in the values of theta that make x equal 1 and x equals 0. Well, that's okay. That's nice and easy. Let me just write out where we are. So we got a of x of theta equals 1/2 of sine of 2 theta plus an arbitrary constant, which we're not really going to need. We want a of 1 minus a of 0. And of course, we know that x of theta is equal to tangent of theta. So basically, we want the values of theta that make tangent of theta equal 1. Tangent of, because we want x equals 1, right? And since x is equal to tangent of theta, we want tangent of theta equals 1, and we want tangent of theta equals 0. Well, if tangent of theta equals 1, then you can work this out by typing in tan inverse or arctan of 1 into the calculator. It's the one with the little to the power of -1 above it. So this tells us that theta is equal to pi divided by 4, since tangent of pi divided by 4 is equal to 1. And when tangent of theta equals 0, it must be the case that theta equals 0, or some multiple of pi added on to 0. So some multiple of pi. But we might as well just use 0. That's fine. So theta equals pi over 4 will give tangent of theta equals 1. So if we put theta equals pi over 4 into here, it's going to give x of theta equals 1, and therefore we're going to get a of 1. So therefore a of 1 minus a of 0 is actually equal to 1/2 of sine of 2 theta. Don't need the plus c because that's going to cancel out. And we're going from theta equals 0 to theta equals pi over 4. And that is equal to 1/2 of sine of 2 times pi over 4. Well, that's just pi over 2. Minus 1/2 of sine of 2 times 0. Well, that's just 0. And of course, 1/2 of, well, sine of pi over 2 is just 1. And therefore, 1/2 of sine over pi over 2 is 1/2. And sine of 0 is 0. So 1/2 of sine of 0 is 0. And so we end up with 1/2. And if we go back and look at what we were actually calculating, we're calculating this guy right here, and therefore, since it's a definite integral, we're actually calculating the net signed area of this curve with the x-axis, and hence it's still an area, and therefore we should include the unit, which is going to be units squared for area. Okay, if that was really hard, don't worry. This takes a lot of practice. If you're not doing the Cambridge exam, maybe the questions you get about integration by substitution will be easier than this. Don't fret. All you need to do is do a bunch of practice. The main step is following along with this. So if you are able to follow along with all the steps in this, then you're in a pretty good spot to end up where you can eventually do them yourself before your exam. Okay, thanks very much for watching. Don't forget to read the notes on the section, and most importantly, do the exercises in the back. The only way to learn maths is to do maths. Can't stress this enough. Thanks very much. See you later. Bye.